Good morning, dear students. Welcome to Bindu Dhadwal chemistry lessons. Our topic for today is biomolecules. These are complex, lifeless molecules which build up living organisms and are required for their growth, maintenance, and ability to reproduce. Some examples of biomolecules are carbohydrates, proteins, enzymes, nucleic acids, lipids, and amino acids. And the branch of science which deals with the study of these biomolecules and their role in living systems is called biochemistry. So first let us study about carbohydrates. Carbohydrates are a class of naturally occurring compounds containing carbon, hydrogen and oxygen, which are primarily produced by plants by the process of photosynthesis. About 70% of solid plant material comprises of carbohydrates. The process of photosynthesis involves the reaction between carbon dioxide and water in presence of sunlight and chlorophyll to form carbohydrates and oxygen as byproduct. The carbohydrates generally have formula CxH2O times. For example, glucose, fructose, cellulose, sucrose, starch, etc. are some examples of carbohydrates. In the earlier days, carbohydrates was considered hydrates of carbon with the formula CxH2O times. For example, glucose, fructose having the formula C6H12O6 and sucrose with the formula C12H22O11 were obeying this formula. However, this definition could not hold good due to the following reasons. There were some molecules, carbohydrates like rhamnose, deoxyribose. They are carbohydrates, formula C6H12O5, C5H10O4 for deoxyribose. They are carbohydrates but do not obey the formula CxH2O times. On the other hand, there are molecules like CH2O, C2H4O2 which obey this formula but they are not carbohydrates. So formaldehyde and acetic acid are not carbohydrates. Carbon is not known to form hydrates. Large polymeric substances where these units combine to form long chains can be broken down to these polyhydric aldehydes and ketones. So from this fact we come to the definition of carbohydrates, which is accepted now. Carbohydrates are defined as optically active polyhydroxy containing many OH groups aldehydes or polyhydroxy ketones or compounds which produce these compounds on hydrolysis. So we can classify carbohydrates as sugars and non-sugars. Sugars will be sweet in taste, for example, sucrose and lactose. And these are called saccharides. Sweet tasting sugars are called saccharides. Non-sugars are tasteless, for example, starch and cellulose. These are tasteless, insoluble in water and amorphous, whereas sugars are crystalline substances which are sweet and water soluble. Systematically, we can classify carbohydrates into monosaccharides, which are comprised of simplest carbohydrates which cannot be hydrolyzed into more simpler compounds. Oligosaccharides, which when hydrolyzed can give 2 to 10 monosaccharides, and polysaccharides, which on hydrolysis will give a large number of monosaccharides. So monosaccharides, when grouped together, to a small extent form oligosaccharides, and to a large extent when they group together they are called polysaccharides. Monosaccharides are simplest carbohydrates which cannot be hydrolyzed into simpler compounds. So it is a single carbohydrate unit. About 20 monosaccharides occur naturally. They generally have the formula CH2O n times. The value of n can be from 3 to 7. That means carbon can be 3 to 7n. For example, ribose is a 5 carbon compound C5H10O5, Glucose is a 6-carbon compound, C6H12O6, and fructose is 6-carbon compound, C6H12O6. Glucose has an aldehydic group as functional group, whereas fructose has ketonic group as functional group. Oligosaccharides will give 2 to 10 monosaccharides on hydrolysis. So disaccharides are those oligosaccharides which give 2 saccharides molecules on hydrolysis. So oligosaccharides can be further classified into di, tri, tetra saccharides. Disaccharides will give 2 saccharides on hydrolysis. For example, sucrose, lactose, maltose are disaccharides. They have the general formula C12H22O11. Trisaccharides, for example, raffinose has the formula C18H32O16. And tetrasaccharides will give 4 saccharides on hydrolysis. For example, stechiose has the general formula, molecular formula C24H42O21. Polymeric compounds, polysaccharides, can be hydrolyzed to give a large number of monosaccharides. For example, cellulose, starch, glycogen. The formula of cellulose and starch is C6H10O5. Monosaccharides. Monosaccharides are polyhydric aldehydes and ketones which cannot be hydrolyzed into simpler carbohydrates. Depending upon the functional group which is present here, if it's aldehyde, the monosaccharide is called aldose, and if it is a ketone, it is called a ketose. So monosaccharides containing an aldehydic group are called aldoses. The CHO group is always present at one end of the carbon atom and is labeled as first carbon. And the monosaccharides containing a keto group are called ketoses, and in all naturally occurring ketoses, keto group is present at second carbon atom, C2. These monosaccharides can be further classified as triose if they contain 3 carbon atoms, tetrose if they contain 4 carbon atoms, pentose if they contain 5 carbon atoms, hexose if they contain 6 carbon atoms, and heptose if they contain 7 carbon atoms. For example, glyceraldehyde is an aldotriose, means the functional group is aldehyde and total carbon atoms are 3. Similarly, dihydroxyacetone is a ketotriose. The functional group is ketone and there are 3 carbon atoms. So, to dihydroxy means there are 2 OH groups attached to 2 carbon atoms. Similarly, tetroses will contain 4 carbon atoms. Examples are erythrose, threose, which are aldotetrose, and erythrulose, which is a ketotetrose containing 4 carbon atoms. Pentose examples are arabinose, ribose, xylose, and lixose, which are aldopentoses. They have aldehyde as functional group. Ribulose, xylulose are ketopentose. They have C double bond O as functional group. Hexoses example glucose, galactose, mannose, and allose are aldohexoses, whereas fructose, sorbose, stegatose, and ceose are ketohexoses containing 6 carbon atoms. Similarly, heptose will contain 7 carbon atoms. Structure of monosaccharides. The simplest monosaccharide are trioses. For example, glyceraldehyde is a aldotriose, aldehydic functional group and 3 carbon atoms, and it contains 2 OH groups. Similarly, dihydroxyacetone is the simplest ketone as functional group and 2 hydroxyl groups and made up of 3 carbon atoms. Similarly, ribose consists of 5 carbon atoms and has aldehyde as functional group and 4 hydroxy groups. And glucose is an aldohexose, means aldehyde is the functional group and the total chain consists of 6 carbon atoms. So it's an aldose hexose. Similarly, fructose is of 6 carbon atoms, but the functional group is ketonic group, which is present at second carbon atom. The rest is similar to glucose. We can also classify them as D and L forms. D and L designations are given when the last chiral carbon atom, that is carbon to which all the 4 groups attached are different, last chiral carbon atom has OH group towards right, will be called D form. For example, simplest aldo triose has aldehyde as functional group, and in this the chiral carbon atom C has OH towards right. This is a D-glyceraldehyde. Based on its name, all other aldohexoses and ketohexoses will be called D if the last chiral carbon has OH group towards right. Similarly, those compounds which have OS group towards left will be called L forms. For example, in the glyceraldehyde structure shown here, the OH group in the chiral carbon atom is present to the left. So it is called L-glyceraldehyde. We must keep it in mind that D does not represent dextrorotatory or levorotatory. For dextro and levo, we give the sign plus and minus, and dextro and levorotatory will show the bending of plane polarized light. A compound which bends the plane polarized light to right will be represented as plus. So this is D-glyceraldehyde, and in D-glucose, the last chiral carbon atom has OH to the right, so it is a D-glucose form. Whereas in fructose, when the last chiral carbon atom has OH to right, it is called D-fructose. In fructose, we have second carbon atom having a double bond O ketonic group attached to it. The OH group attached to last chiral carbon atom, if it is projected to right, it is D form. If it is projected to left, it is L form. And this D and L do not represent dextro or levorotatory. Optical activity will be represented by plus if it is rotating towards right, if it's dextrorotatory, and will be represented as minus if they direct the plane polarized light to left. So if it direct plane polarized light to left, it's levorotatory and represented as minus form. Presence of asymmetric carbon atoms. So glucose has 4 chiral carbon atoms. Now, if there are n chiral carbon atoms, this is glucose, carbon atom number 2, 3, 4 and 5. These 4 carbon atoms are chiral. The 4 groups attached to this carbon are all different from each other, so they are chiral carbon atoms. Now, if there are n chiral atoms in a compound, it will have 2 raised to power n optical isomers. So that means glucose having 4 chiral carbon atoms will have 2 raised to power 4, that is 16. 2 into 2, 4 into 2, 8 into 2, 16 optical isomers. The 3 of these 16 aldohexoses of glucose are D-glucose, D-galactose and D-mannose. The difference arises only in the positions of OH towards left or right, otherwise the formula is the same. So in D-glucose, we have the 3rd carbon having OH to the left and last 5th chiral carbon atom having OH to the right. So it's D-glucose, it's optically active. D-galactose has the similar structure. The difference is at C4, the OH is on the left, whereas in D-glucose it is towards the right. Rest of the formula is the same as that of D-glucose. Similarly, D-mannose, here the difference lies at the 2nd carbon atom. The OH of 2nd carbon atom in mannose is to the left, whereas in glucose it is to the right. So by remembering the structure of one group and just remembering the differences, we can write down the structures of different compounds. Now, when we carry out some reactions of these open chain structures, we find that sometimes they are not undergoing reactions particular to their aldehydic functional group or ketone functional group. This suggests that when these compounds are existing as in dimeric form, they are not in the open chain structure, they are in the closed chain cyclic structure. Some properties of glucose suggest that glucose does not have open chain form structure. When either of the two forms, alpha D glucose and beta D glucose, are dissolved in water and allowed to stand, these will get converted into the other form. Alpha will change to beta or beta will change to alpha and form an equilibrium mixture of both alpha D and beta D forms. So this is when it is purely alpha D, the specific rotation angle is 111 degrees. The angle to which the plane polarized light is bent is towards right at an angle of 111 degrees. But the beta D glucose in pure form will bend it to 19.2 to right. And when this open structure is dissolved in water and allowed to stand, they form an equilibrium mixture containing both alpha and beta, 36% alpha and 64% beta. And the equilibrium mixture that is formed will be having angle of rotation of plus 52.5. This will change to this angle, or this angle will also change to this angle if dissolved in water and kept on standing. So this spontaneous change that occurs by itself in specific rotation of an optically active compound with the time to an equilibrium value is called Muta rotation. This is dissolved in water, allowed to stand, it will itself change its angle from this to this. So this is called Muta rotation. This process is called Muta rotation. So we see alpha D glucose will change to equilibrium mixture. Its specific angle rotation will change from plus 111 to plus 52.5. Similarly, beta D will also change from 19.2 to 52.5 if dissolved in water and kept to stand. So it has been found that these monosaccharides from open, when they change to cyclic structure, they form this equilibrium. The probability of forming, it has been found that these monosaccharides exist in form of cyclic structures. We know that aldehydes and ketones react with the hydroxyl group to form hemiacetals and acetals. That is, the electrons will be moved towards oxygen. The H of OH group will go to the oxygen, whereas the OR part will go to the carbon. So as a result, H has gone here and formed OH, and OR is attached to carbon. So this is hemiacetal. And on reacting with another alcohol molecule, this OH and ROH will combine to form water, and OR dash gets attached here. So when two OR dash groups are attached, it's called acetal. So in monosaccharides, because we have aldehydic group as well as hydroxy group, so intramolecular hemiacetal formation occurs. So during cyclization, see, this is an open chain structure. This is the aldehydic group. These are the hydroxy group. So within the molecule, a hemiacetal structure will result. These electrons will move to this side, and H of the OH of fifth carbon atom will go to attach itself to oxygen, whereas the O will attach to carbon. So as a result, from open chain, it changes into a cyclic closed structure. So first carbon is attached to fifth carbon through oxygen. This becomes a closed chain structure of 1, 2, 3, 4, 5, 6 members. So it's a 6-membered ring. So in the cyclic structure that is formed on the first carbon, if OH is towards the right, it is an alpha form, and if OH first on the first carbon is towards the left, it is a beta D glucose. So the same D plus glucose in open form, when changes to cyclic form, can have OH either to the right, then it is alpha, or OH to the left, then it is beta. This occurs only at first carbon atom. So these two forms, they are not mirror images of each other. They are simply isomers of each other. Such isomers which differ with each other only with the respect to the position of OH group attached to the first carbon atom are called anomers. So such pairs of optical isomers which differ in the configuration only around C1 atoms are called anomers. These two forms of optical isomers are not mirror images, they are not enantiomers, they are called anomers. And this carbon number 1 is called anomeric carbon. This carbon number 1 is called anomeric carbon or glycosidic carbon, because on reacting with methyl alcohol, it can form an ethereal linkage which is called glycosidic linkage. Okay, now this form of representation of cyclic structure is called Fischer representation, Fischer structure. If we represent it in the form of a ring like this, then it is called Havoc structure. This is called Havoc structure. So in Havoc structure, we always place oxygen at this position, and the first carbon atom will be attached here. So first carbon number 1, then 2, 3, 4, 5 carbon, and because it's attached to 5th carbon through oxygen, so this completes the ring. And on the 5th, there are 2 groups attached, H and CH2OH. So these are the 2 positions. Now whatever groups are attached on the left side are placed on the upward in the Havoc structure, and the groups which are attached on the right side are placed on the downward side. So we know that in alpha D glucose form, the OH attached to first carbon is on the right side. So we have placed OH down and placed H above carbon. Similarly, in the third position, we have OH on the top, so left. So what is placed in the left is placed upwards in the Havoc structure. So this is how we write the structure. C, after O, we write first carbon atom C. H is on the left, so H is placed up, OH down. Then H up, OH down. Then OH up, because it's on the left, then H down. Then H up, OH down, and in the 5th carbon atom, we place CH2OH up and H down. That is HCH2OH during this presentation comes to the left. So this is the Havoc structure of alpha D glucose. Similarly, for Havoc structure for beta D glucose, will be having OH towards the left. So OH is placed on the top here and H is placed bottom. The rest of the structure is similar to this structure. Similarly, in fructose, the 6th OH will get added to the 2nd carbon double bond oxygen group and form a 6-membered ring. So the 6th OH gets attached here. When the OH comes to the right side, it is alpha D fructose. When OH comes to the left side, it is beta D fructose. And again, in the Havoc form, we will write it as a 6-membered ring. So after oxygen, the first carbon is the carbon number 2, because first carbon is attached to it on the left side. So CH2OH is placed on the top, OH at the bottom of this carbon. Then third carbon has OH to the left, so OH is placed up. Fourth has OH on the right, so it's placed down. Fifth has OH on the right. And sixth one has 2 hydrogens, so they are placed. So this is the Havoc structure of alpha D-fructopyranose. This is pyranose because it's forming a 6-membered ring. Sometimes this is in free state, it forms a pyranose ring. But when it is attached to another monosaccharide and is forming a disaccharide, then the ring that is formed is of 5 carbon atoms. The OH of the 5th carbon rather than 6th gets attached to the OH double bond O of the 2nd carbon, and a 5-membered ring is formed. As this ring is similar to the structure of a furan, this type of structure is called Furanose structure, and it is written like this. So after oxygen, the first carbon is having CH2, OH to the left, so we have placed it on the top and OH on the right. So this form of structure is called Furanose structure. It consists of 6 carbon atoms, and the original functional group was ketonic. It came from fructose, so this compound will be called fructofuranose. So practice all these facts and structures at home. That's all in today's video. If you like the video, please do share and subscribe. Thank you. Have a nice day.